Okay, so we'll be starting with series resonance. What do you mean by series resonant circuit first of all? Let me write the series RLC. Okay, so a resistor, inductor and a capacitor. AC voltage is applied to it. Let me just write it as V. This is R, L and C. So what do you mean by series resonant circuit? Anybody? When do I say it is resonant? When inductive reactance is equals to capacitive reactance. Okay, so that's what first we are going to prove it here. So what exactly you're going to study in this particular topic? Series resonance, variation of current, voltage with frequency, selectivity and bandwidth, then Q factor. Okay, so then again you will be studying parallel circuit, so that we will do later on. So first tell me, what is the overall impedance here? R plus, R plus, please write it like this. R plus JXL minus JXC. Okay. What is XL? Inductive reactance. What is XC? Is equals to. How will you write in terms of angular frequency and inductance value? Omega L or 2 pi FL. F is the frequency. And then how do you write the capacitive reactance? 1 by omega C or 1 by 2 pi FC. Okay. So when you see this particular equation, let me write it as 1. When do you have the maximum current flow? When do you have maximum current flow? You have R component, XL component, XC component. So if you are finding the magnitude of this impedance, how will you find square root of R square plus XL minus XC whole square? Correct. So now if I can reduce this XL minus XC to 0, what will I have? Impedance is equals to only resistance. That means V by R will be your current. So I can get maximum current when XL is equals to XC. This particular point is called as what? Resonant condition. Okay. So please understand. Please write down. When XL is equals to XC, impedance will be R. The whole circuit impedance will be resistive in nature. Okay. I'll show that again later on. Okay. So maximum current is achieved. When do I achieve maximum current? At resonant condition, Z equal to R or XL equal to XC. So this condition is referred as resonant condition. Please understand. So if I want to find this resonant frequency, what should I do? I will substitute the equation for XL and XC here. What was the equation for XL? 2 pi FL. What is the equation for XC? 1 by 2 pi FC. So I will keep only F here. So I'll bring all these F this side, 2 pi L to the right side. Okay, so what do I have? F square divided by 1 by 4 pi square LC. That means, again, since it is resonant condition, I will write it as F naught. Okay, so what will be F naught now? 1 by 2 pi root LC. So what is this frequency? What do you call it as? Resonant frequency. Okay. So at resonant frequency, what do we know? Z is equals to R. XL is equals to XC. Also, there is a term power factor. Anybody? What is power factor? Cos phi. What is that phi actually? Any idea? Angle between, correct, angle between V and final I. All are vectors. Okay. We are considering resistance, inductor and capacitor. I can represent them using phasors. This V and this I, sorry, V is your applied voltage. Remember, I is what? Resultant current, not just for the resonant condition. This diagram I have written for any series circuit. Okay, this is the resultant current applied voltage. So power factor is given by cos phi. Cos phi is equals to 1 for resonant condition only. Please write down. Usually it can be anything. Okay, if it is only capacitor or only inductor, do you know what will be the cos phi? Only RL or only RC? What will be cos phi? Current will be, vector will be directly, sorry, it is perpendicular to V. What will be phi value? 0. Sorry, 90. So cos phi will be 0. Power factor value will be 0. Please understand in that manner. Okay. So now I have written about power factor, then resonant condition. Next component is Q factor. Okay. This Q factor, it is not like a SI unit or something. It is a figure of merit. Okay. It mainly tells you about selectivity of this particular circuit. Q factor is a figure of merit, tells you about selectivity. Okay. So in this resonant circuit, what are the two storage elements you saw? Inductor as well as capacitor. Okay. Inductor in which field? Any idea? Inductor and capacitor. Remember, capacitor always in electric. Inductor is always in magnetic. Okay. That's how they store the energy. The definition for the Q factor will be efficiency at which these two energy storing elements store the energy. Okay, that's a definition, but that's not exactly standard way. That's how you are supposed to understand. Q factor tells you detail about how much energy is stored by these two elements, L and C, with respect to power dissipated. Which will dissipate the power? Resistor. That's it. So how exactly you're going to find the equations now? Power dissipated, power stored by L or power stored by C divided by power dissipated by the resistor. Okay. So write down the definition for Q. We will be writing it as equation over 2 pi maximum energy stored per cycle. Per cycle of what? Per cycle of AC signal. Okay. Divided by energy dissipated per cycle. So now we will have to write Q factor for LR circuit and then RC circuit. Okay, so Q factor for LR, just consider a AC circuit with only L and R. This is some, let me write it as V1 since I have written V for resonant condition already. The Q factor is given by omega L divided by R. Directly, okay. So this is impedance of, sorry, not impedance, inductive reactance divided by resistance. So usually the expression will be XL by R. If it is capacitive, equation will be XC by R. That's what I will write here. So Q factor in case of RC circuit, if the circuit is in this manner, Q factor will be XC by R. Can somebody help me with the expression? 1 by omega C into R. Please understand. Okay. So this is about the Q factor or quality factor. So if I want to find omega naught at resonant condition, what is omega naught? No, see, F naught is what? 1 by 2 pi root LC. Correct? So what I have to do to get omega naught? I just have to bring 2 pi here. So that implies omega naught is equals to 1 by root LC. Okay. So now using this, what I can get is Q factor for inductor. Now I will write here as inductor. What was the Q factor we had? Omega naught L divided by R. So now instead of omega naught, let me write it as 1 by root LC into L by R. So how can I rewrite it? 1 by R L This L, can I write it as product of two square roots? Yes. So when I cancel it out, equation will be 1 by R square root of root LC. Okay. Similar way, if I want to write Q naught for what? Capacitor. When I write capacitor inductor, please remember there is a resistor involved. Okay. I'm not simply writing for one element alone. So this is given by 1 by omega naught CR. Again, I will write omega naught. 1 by omega naught is 1 by 1 by root LC. So that I'm writing here. Omega naught I have written CR. So what will be the expression again? What will be the expression? 1 by R into square root of, again same, correct? Yes. So this will be the Q factor for any resonant series circuit. Sorry, series resonant circuit. Please understand. Okay. For any series resonant circuit having L, R, C, Q factor will be 1 by R into square root of LC. So this particular question was asked before also. So please you have to be careful with Q factor. Okay. So Q factor is over. Next, we have to write equation in terms of voltage and current for series circuit. So previously I have mentioned inductor, capacitor as C. Now let me write it as XL, JXL. What should I write here? Minus JXC. No confusion, right? About minus. Okay. R is VR. Voltage across XL is VL. Across capacitor VC. Overall applied voltage is V. What will be the expression? V is equals to VR plus VL plus VC. No change. So simply I will consider the current as some I into R plus J XL minus XC. Is that right? Or any change? Okay, no change. So at resonance, what will be I equal to? At resonance, what will be I equal to? I max. That is V by R. So I can write it as I max, correct? Yes or no? I get maximum current at series resonance. So instead of writing it as small I, I'm going to mention it as I max. What will be the voltage across VL in terms of current and XL? Voltage across VL. Reactance is JXL. Current is at resonance. I max. So I will write it as I max. Same thing I will write I max J XL. I want to write it as omega L. What is this I max equal to? V by R. So again I will write V by R. J here omega L. What is omega L by R? Q, correct? Q. So since we have considered everything at resonance, I will consider omega naught and then Q naught. Okay. Similarly, I want to find VC. What is VC? I max into minus JXC. So when I write again minus I max J 1 by omega naught C, is that right or not? Yes. So how will I get I max equal to? For C, no change, right? It is just V by R and then 1 by omega naught C. 1 by R into omega naught C is, sorry, I forgot J here. What is 1 by R into omega naught C? Q naught, correct? So that I will write here equal to minus JV Q naught. See, now be careful. What is V? Applied voltage, correct? Applied voltage. Q is something extra, correct? Q is something extra. So if in case Q is some number, what do you feel it is doing here? V is equals to the voltage across inductor is equals to applied voltage into some constant. What is happening here? What do you call this process as? You have given V, but you are getting back V into Q naught. So what do you think happened here? What? Amplification. Okay. So here these Q naught are considered to be amplifying parameters for V. Okay. So what exactly is happening? Amplification of applied voltage. So that's why we say at resonant condition, we can consider this circuit as amplifier. Why? Because it is amplifying the voltages. Okay. So please write down that particular point. At series resonance condition, voltage across L and C are maximum. And also Q naught is very high at resonant. I have mentioned Q naught, so need not write resonant. Anyhow, Q naught is quality factor is very high at resonant condition. So series resonant circuit can be considered as voltage amplifiers. Do not just write amplifier, voltage amplifier, because it is amplifying the voltage here. Okay, understood why we are calling it as amplifier? So this is one of the questions you will get. How do you see that series resonant circuit is acting as amplifier? You will have to start from the first itself, from the beginning, from the resonance XL equal to XC, because that is required for finding Q factor. Okay, so that's one part. Next one, we need to find the bandwidth. What do you mean by bandwidth? What do you mean by bandwidth? Difference between any two frequency with some given characteristic. Okay, so now here we have to find bandwidth. So what do you think here it might be? F naught is resonant frequency. Remember, okay? Resonant frequency is F naught. That's when you get the maximum amount of current. What is bandwidth? See here what we do. We consider half power. Okay? We want to know within which frequency our series resonance circuit works like a amplifier as of now. Okay? So we consider half power. So P by 2. What is exactly P? Power, what is the overall equation at resonant condition? Okay, leave resonant condition. Usually, what is power? Either V square by R or I square R. Okay, so now I will write I naught square R divided by 2. Okay, so now if I take the what? The square root of this, what will I get? I naught by root 2 into square root of R. Okay. So what exactly we are going to do now? We are going to find the frequency range. Okay. Range of frequency at half power. That's it. We are going to find the range of frequency at half power or at the point where current is I naught by root 2. Okay. Understand where current is I naught by root 2. Why I'm saying that? Because from the circuit, I can write this particular graph. X-axis, I'm considering the frequency. Y-axis, I'm considering the current. The graph will be like this. Can somebody tell me what is this particular point where I have the maximum current? What is this particular point? Resonant frequency. I will write here. What will be this particular point? I naught. Yeah, I max or I naught. Let me write because previously I have written I max. No need to get confused. So I naught. What did I write here? We are finding the power at, sorry, we are finding the bandwidth at half power. Half power means with respect to current, it will be I naught by root 2. Okay. So this particular concept, usually we call it as 3 dB concept. Okay. Usually we write power and everything in terms of dB. So what will be 10 log of 2? Anybody? 10 log of 2 or 20 log of root 2. What will be 10 log of 2? 3.02 dB. So that's why we call this concept as 3 dB concept. Okay. So somewhere here, not exactly half, somewhere here 0.707 or I naught by root 2. At this particular point, I will mark with respect to frequency. I will write it as F1, F2. So the bandwidth is given by what? F2 minus F1. That's it. Always remember bandwidth means range of frequency. Okay. So here F2 is nothing but up frequency and F1 is lower cutoff frequency. And what did we observe from the graph? We observed current increases at till resonant point, then again it decreases. Okay. So F naught is a resonant frequency. If anybody asks you the definition, what you have to say, the frequency at which current is maximum. Okay. So this is about the bandwidth, how exactly you can find, how exactly you can consider the half power condition. Everything we are considering under resonance condition only. Remember that. Okay. Otherwise, I should have written what? I naught square into Z. Instead, if not resonant, okay, then I should have written it as I naught square into Z. So one more last topic in this series resonance. Okay, do you want to write the definition for bandwidth? Let me write first. Definition for bandwidth you can write down. I have written the equation, the same thing. Range of frequencies at which power in the circuit is half of its maximum value. Okay, so that's the bandwidth. Do you know the any equation for bandwidth? You can use F2 minus F1. Okay, in case if they give you where exactly you have the half power for upper cutoff and lower cutoff frequency. Okay, next parameter we are going to study is selectivity. Again, the selectivity and Q factor are very much related. So now I'm speaking about selectivity. Its definition is resonant frequency divided by bandwidth. That's the definition. Okay, selectivity is ratio of resonant frequency over bandwidth of particular resonant circuit. So at resonant, sorry, at resonance, I should have written at resonant frequency also fine. At resonance, I can write F naught by. We have expression for bandwidth as R by omega L. Okay, R by omega L is one of the expression for bandwidth. So the same thing I will write here, R by 2 pi L, that will be 2 pi F naught divided by, sorry, 2 pi F naught L by R. Is that correct? 2 pi F naught L by R. Okay. So have you seen any expression like this before, or omega L by R? Omega L by R, it is Q naught. Okay. So the main objective here is just to mention, as per the value concerned, selectivity, sorry, omega is 2 pi F. No, this is for the, sorry, no. R by 2 pi L, not 2 pi FL. 1 by 2 pi into R by L is the bandwidth. Sorry, 1 by 2 pi into R by L is the bandwidth. Okay. So selectivity value is equals to quality factor. Okay. So you can write down the definition as ability of resonant circuit to distinguish between desired and undesired frequency. That's it. Okay, so desired frequency is what? Out of this bandwidth, I want F naught to be the frequency so that current is maximum. So that is about the selectivity.